This chapter introduces fundamental definitions and background concepts crucial for understanding reinforcement learning from human feedback, RLHF. It begins with a language modeling overview, explaining how modern models like transformers use autoregression and self-attention to predict token sequences, trained by minimizing negative log likelihood, NLL, loss. Key machine learning definitions include callback labeler, KL divergence, a measure of difference between probability distributions. Natural language processing, NLP, definitions cover essential terms like prompt, completion, including chosen and rejected variants, preference relation, and policy, as a distribution over completions. Reinforcement learning, RL definitions detail concepts such as reward, action, state, trajectory distribution, policy as an action selection strategy, discount factor, value function V, Q function Q, and advantage function A. It also discusses policy condition values and the primary RL goal of maximizing expected cumulative reward, including the finite horizon case. The concept of on-policy data in the RLHF context is clarified. A specific RLHF definition provided is the reference model PyRef, used for regularization. Finally, an extended glossary defines synthetic data, distillation, teaches student knowledge distillation, including its loss function, in-context learning, ICL, and chain of thought, COT, prompting 3 definitions and background. This chapter includes all the definitions, symbols, and operations frequently used in the RLHF process, and with a quick overview of language models, the common optimization target of this book. 3.1 Language Modeling Overview. The majority of modern language models are trained to learn the joint probability distribution of sequences of tokens, words, subwords, or characters in an autoregressive manner. Autoregression simply means that each next prediction depends on the previous entities in the sequence. Given a sequence of tokens x equals x1, x2, xd, the model factorizes the probability of the entire sequence into a product of conditional distributions. The formula p theta, x, represents the probability of a sequence x under model theta as the product, from t equals 1 to t, of the conditional probabilities p theta, xd x1, xd minus 1, meaning the probability of the TTH token given all preceding tokens. In order to fit a model that accurately predicts this, the goal is often to maximize the likelihood of the training data as predicted by the current model. To do so, we can minimize a negative log likelihood, NLL, loss. The formula LLM, theta, represents the language model loss for parameters theta as the negative expectation over data d of the sum, from t equals 1 to t, of the log probability of the true token xd given the preceding context xt, according to the model p theta. In practice, one uses a cross-entropy loss with respect to each next token prediction, computed by comparing the true token in a sequence to what was predicted by the model. Implementing a language model can take many forms. Modern LMs, including ChatGPT, Claude, Gemini, etc., most often use decoder-only transformers sauce. Attention is all you need, in Neural Information Processing Systems, 2017. The core innovation of the transformer was heavily utilizing the self-attention, SOS, neural machine translation by jointly learning to align and translate, COA-vol, ABS. 2014, mechanism to allow the model to directly attend to concepts in context and learn complex mappings. Throughout this book, particularly when covering reward models in Chapter 7, we will discuss adding new heads or modifying a language modeling, LM, head of the transformer. The LM head is a final linear projection layer that maps from the model's internal embedding space to the tokenizer space, aka vocabulary. Different heads can be used to reuse the internals of the model and fine-tune it to output differently shaped quantities. 3.2 ML definitions. Callback labeler, KL divergence, DKL, PQ, also known as KL divergence, is a measure of the difference between two probability distributions. For discrete probability distributions P and Q defined on the same probability space X, the KL distance from Q to P is defined as. The formula DKL, PQ, defines the callback labeler divergence from distribution Q to P as the sum over all X in the space X, of P, x times the logarithm of the ratio p x slash q x. 3.3 NLP definitions. Prompt X, the input text given to a language model to generate a response or completion. Completion Y, the output text generated by a language model in response to a prompt. Often the completion is denoted as YX. Chosen completion, IC, the completion that is selected or preferred over other alternatives, often denoted as ichosen. Rejected completion, the disfavored completion in a pairwise setting. Preference relation, a symbol indicating that one completion is preferred over another, e.g., ichosen, irrejected. Policy pi, a probability distribution over possible completions, parameterized by theta, pi theta, yx. 3.4 IL definitions. Reward R, a scalar value indicating the desirability of an action or state, typically denoted as R. Action a decision or move made by an agent in an environment, often represented as A, where A is the set of possible actions. State S, the current configuration or situation of the environment, usually denoted as SS, where S is the state space. Trajectory tau. A trajectory tau is a sequence of states, actions, and rewards experienced by an agent. Tau equals S0, A0, R0, S1, A1, R1, SD, AT, RT. Trajectory distribution, P, tau pi. The probability of a trajectory under policy pi is defined as the product of the initial state probability P, S0, and the product over time T equals 0 to T1 of the policy's probability of taking action at given state cent pi at cent, and the environment's transition probability P, cent plus 1 cent at. Policy pi, also called the policy model in RLHF. In RL, a policy is a strategy or rule that the agent follows to decide which action to take in a given state. Pi, a S. Discount factor, gamma. A scalar 0 less or equal to gamma less or equal to 1 that exponentially downweights future rewards in the return, trading off immediacy versus long-term gain, and guaranteeing convergence for infinite horizon sums. Sometimes discounting is not used, which is equivalent to gamma equals 1. Value function, V, a function that estimates the expected cumulative reward from a given state. V(S) represents the expected sum of discounted future rewards starting from state S, following a given policy. Q function, Q, a function that estimates the expected cumulative reward from taking a specific action in a given state. Q, S, A represents the expected sum of discounted future rewards starting from state S, taking action and following a given policy thereafter. Advantage function, A, the advantage function AS, quantifies the relative benefit of taking action in state S compared to the average action. It's defined as AS, A equals Q, S A V S. Advantage functions and value functions can depend on a specific policy, pi, S A. Policy condition values. Across RL derivations and implementations, a crucial component of the theory and practice is collecting data or values conditioned on a specific policy. Throughout this book, we will switch between the simple annotation of value functions et al. V, A, Q, G, and their specific policy condition values, V pi, A pi, Q pi. Crucial is also in the expected value computation is sampling from data D pi that is conditioned on a specific policy, D pi. Expectation of reward optimization. The primary goal in RL, which involves maximizing the expected cumulative reward. The formula shows the objective is to maximize, over policy parameters theta, the expected sum of discounted rewards, gamma t RT, over an infinite horizon, t equals 0 to infinity, where states S are sampled from the state distribution rho pi induced by policy pi theta, and actions are sampled from the policy pi theta itself. Where rho pi is the state distribution under policy pi, and gamma is the discount factor. Finite horizon reward J pi theta. The expected finite horizon discounted return of the policy pi theta, parameterized by theta, is defined as J pi theta represents the expected total discounted reward, sum of gamma t RT from t equals 0 to t, for trajectories tau sampled according to the policy pi theta, where T is the finite horizon. On policy. In RLHF, particularly in the debate between RL and direct alignment algorithms, the discussion of on-policy data is common. In the RL literature, on-policy means that the data is generated exactly by the current form of the agent. But in the general preference tuning literature, on-policy is expanded to mean generations from that edition of model, e.g., an instruction tune checkpoint, before running any preference fine-tuning. In this context, off-policy could be data generated by any other language model being used in post-training. 3.5 RLHF-only definitions. Reference model PyRef. This is a saved set of parameters used in RLHF where outputs of it are used to regularize the optimization. 3.6 Extended glossary. Synthetic data. This is any training data for an AI model that is the output from another AI system. This could be anything from text generated from an open-ended prompt of a model to a model rewriting existing content. Distillation. Distillation is a general set of practices in training AI models where a model is trained on the outputs of a stronger model. This is a type of synthetic data known to make strong, smaller models. Most models make the rules around distillation clear through either the license, for open-weight models, or the terms of service, for models accessible only via API. The term distillation is now overloaded with a specific technical definition from the ML literature. Teacher-student knowledge distillation. Knowledge distillation from a specific teacher to student model is a specific type of distillation above and where the term originated sauce. Distilling the knowledge in a neural network. Archive preprint RZIV 1503, 02531, 2015. It is a specific deep learning method where a neural network loss is modified to learn from the log probabilities of the teacher model over multiple potential tokens/logits, instead of learning directly from a chosen output. An example of a modern series of models trained with knowledge distillation is Gemma 2 sauce. Gemma 2, improving open language models at a practical size. Archive preprint RZIV 2408, 00118, 2024. Or Gemma 3. For a language modeling setup, the next token loss function can be modified as follows sauce. On-policy distillation of language models, learning from self-generated mistakes, in the 12th International Conference on Learning Representations, 2024, where the student model p theta learns from the teacher distribution p. The formula LKD, theta, defines the knowledge distillation loss for parameters theta as the negative expectation over data d of the sum, from t equals 1 to t, of the teacher distribution's probability p asterisk, xd/xt, multiplied by the log probability assigned by the student model p theta, xd/xt. In context learning, ICL, in context here refers to any information within the context window of the language model. Usually, this is information added to the prompt. The simplest form of in-context learning is adding examples of a similar form before the prompt. Advanced versions can learn which information to include for a specific use case. Chain of thought CoT. Chain of thought is a specific behavior of language models where they are steered towards a behavior that breaks down a problem in a step-by-step form. The original version of this was through the prompt Let's Think Step by Step. SOS. Chain of thought prompting elicits reasoning in large language models. Advances in Neural Information Processing Systems, Vol. 35, pp. 24824 for 837, 2022.